Welcome to this presentation on the dual nature of electron and quantum mechanical concept. I am Miss Yanjana Sunahale from the Department of Chemistry, Pandit Sundarlal Sarma Open University, Chhattisgarh, Bilaspur. In this session, we will explore how electrons behave as both particle and wave and how modern quantum mechanicals explain this interesting behavior. Contained in this presentation, we will cover the dual nature of electron, the de Broglie hypothesis, its derivation, experimental proof, the Heisenberg uncertainty principle, the Schrodinger wave equation, and finally the meaning of the wave function and orbitals. Next, dual nature of electron. Electrons show dual nature, meaning they behave both like particle and like wave. As particle, they possess mass, charge, and momentum, and they can collide and inject electron in the photoelectric effect. As wave, electron undergoes diffraction and interfraction, and they have a specific wavelength. Thus an electron is not pure a particle nor pure a wave, it is a both. Next, de Broglie hypothesis. Louis de Broglie proposed that every moving particle is associated with a wave. This is known as the metal wave concept. According to his equation, the wavelength of a particle is equal to Planck constant divided by its momentum mv. This idea formed the foundation of quantum mechanics. Next, derivation of de Broglie equation. Derivation of the de Broglie equation, which explain the wave nature of matter. Louis de Broglie proposed that matter like electron behaves not only as a particle but also as waves. To prove this idea, he compared a moving particle with a photon and used two important equation, Einstein's energy relation and Planck equation relation. Let's start with the basic equation. Step first, Einstein energy equation. For a photon, the total energy is given by E is equal to mc square. At the same time, energy of the same photon is also given by Planck relation E is equal to hv, where h is a Planck constant and v is a frequency. Second step, equate both expression for energy. Since both expression represent the same energy, we can equate them. So mc square is equal to hv. Now we know that frequency v can be written as c divided by lambda. So we substitute v is equal to c by may lambda. This gives us mc square is equal to hc by may lambda. The next step, simplifying the equation. Divided both sides by c, we get mc is equal to h by may lambda. But we also know that for a photon, momentum p is equal to mc. So we can relate mc with p. This gives us the simple and important relation. P is equal to h by may lambda. And if we rearrange this, we get lambda is equal to h by may p. This is the wavelength of a photon. Then step 4, de Broglie hypothesis. Now de Broglie said something very important. If light, which is a wave, can behave like a particle, then a particle such as an electron should also behave like a wave. So the sum formula must also apply to matter particle. Therefore, for any particle with momentum p, lambda is equal to h by may p. The next step, now substitute momentum of a particle. For matter, momentum p is equal to mass time velocity. So p is equal to mv. Putting this into the equation, we get lambda is equal to h by may mv. The next, and this is the de Broglie matter wave equation. So finally the expression is lambda is equal to s divided by mv. This equation tells us the any moving particle have a wavelength associated with it, and This wavelength becomes signification only for very small particles such as electron. The next, Davison-Graham experiment. The Davison-Graham experiment proved the first experiment proof of the wave nature of electron. When electrons were directly at a nickel crystal, they produce a diffraction pattern. This behavior is characteristic of wave conformation de Broglie hypothesis. The next, Heisenberg uncertainty principle. The uncertainty principle states that it is impossible to know both the exact position and exact momentum of an electron simultaneously. This more accurately we determine on quantity. The more uncertainty, the other, because this principle proves that electron cannot have fixed circular path. We know about Schrodinger wave equation. The Schrodinger wave equation is a fundamental equation in quantum mechanics. It describes how the wave function of an electron behaves. Solving the equation gives us quantized energy level and atomic orbital. We derive of Schrodinger time-independent wave equation. Schrodinger used wave mechanics based on the idea that matter behave like a wave. Just as de Broglie suggested, let us start the derivation step by step. First step, start with the classical wave equation. A generally one-dimensional wave can be written as psi of x and t equal to a multiplied by sin of kx minus omega t. This pi is called that wave function. Here k is the wave number is equal to 2 by me lambda and omega is the angular frequency is equal to 2 pi v. Next step, take the second derivation. If we take the second derivation of psi, we represent 2x, we get d square psi by me dx square is equal to minus k square psi. Take the second derivation of psi with respect to x, we get del square psi by me del x square is equal to minus k square psi. Similarly, the second derivation of psi with respect to time gives psi square. Similarly, the second derivation of psi with respect to time gives del square psi by me del t square is equal to minus omega square psi. These two equations show the mathematical behavior of a wave. The next step, use de Broglie and Planck relation. Now we connect the wave with the particle. For de Broglie, P is equal to mv is equal to h by me lambda is equal to h cross k, where h cross is equal to h by me 2 pi. So k is equal to p by me h cross. Similarly, from Planck relation, E is equal to hv by me h cross omega. Thus, V is equal to E by me h cross. The next step, substitute k and omega in the derivation. Since k is equal to p by me h cross and omega is equal to k by me h cross, we can write del square psi by me del x square is equal to minus कोष्टक में p by me h cross का whole square psi is equal to minus p square by me h cross square psi. Step 5. Use the total energy of the particle for a particle of mass m. The total energy is E is equal to kinetic energy plus potential energy. So, E is equal to P square by 2m plus V of x. Rearranging, we can write P square by 2m is equal to E minus V. Then step 6. Substitute P square into the wave equation. We have P square is equal to 2m कोष्टक में E minus में V. Substitute this in the space derivation equation. So we can write del square psi by में del x square is equal to minus 2m कोष्टक में E minus V by h cross square of psi. Rearrange del square psi by में del x square plus 2m by में h cross square e minus में v का of psi is equal to 0. The next final form of Schrodinger time independent wave equation. If we multiply the entire equation by minus h bar squared by 2m, we finally obtain the famous Schrodinger time independent wave equation. Minus h square by me 2m d square psi by me dx square plus v of xi is equal to e psi. This is the standard form of Schrodinger equation in one dimension. Three-dimensional general form. In three-dimensional, the equation becomes minus h square by me 2m del square psi plus v psi is equal to e psi. The Laplacian represents the curvature of the wave function in 3D space. Meaning of Schrodinger equation. In this equation, the first term represents the kinetic energy, the electron, while the second term represents potential energy. On the right hand side, we have total energy multiplied by the wave function. This balance forms the basis of quantum mechanical solution. Wave function psi. The symbol psi is called the wave function. It is a mathematical function that describes the behavior of an electron wave. Psi does not have any direct physical meaning. It simply contains all the information about the electron. Then next, probability density, psi square. When we square the wave function, we get psi square, which has a clear physical meaning. Psi square gives us the probability of finding an electron in a particle region. It is always positive. Whenever psi square is a high, that electron is more likely to the present. The next, orbital modern concept. An orbital in a three-dimensional region around the nucleus where the probability of finding an electron is maximum. Orbitals do not have fixed path. Their shape and size are defined by the wave function psi and psi square. Different orbitals have different shapes. S orbital are spherical, p orbital are dumbbell shaped, d orbital are double dumbbell shaped, and f orbital are more complex. We can see in this diagram. So electrons are not simple particle. They act like wave too, and quantum mechanical explain everything about them. Rest of the topic we will discuss in the next class. Thank you so much.